In this lecture, I'm going to be talking more about definite integrals. First, we want to talk a little bit about the midpoint rule, just because we've only talked about approximating the area under a curve using right endpoints and left endpoints. And we found that in doing so, sometimes those gave us an overestimate or an underestimate, and midpoints can often prove to give us a pretty good approximation. So if we're just interested in approximating an integral, it would be good to use a midpoint approximation. So for this example, we want to go ahead and use the midpoint rule to approximate the integral from 0 to 2 of x over x plus 1 dx using 5 different rectangles. So the idea here is I've got my interval from 0 to 2. I want to divide it into 5 rectangles. So I've got 1, 2, 3, 4, 5 different pieces there. Now since my interval here goes from 0 to 2, my width is 2 minus 0 over n, which in this case is over 5, so we have 2/5. So I know that this first interval goes from 0 to 2/5. The next one is 4/5, then we have 6/5, 8/5, and the last one would be 10/5, which is equal to 2. Okay, so the midpoint rule says that our sample point that we're going to pick isn't going to be the left endpoint or the right point, but it's going to be the midpoint of the interval. And we're going to use that midpoint plugged into our function to get the height of each one of our rectangles. So the formula for our midpoint is just the average of the two endpoints of the interval. So we add them together and divide by 2. So 2/2 plus 0 divided by 2 is going to give us 1/5. We can also see that halfway between each of these different intervals, here I'm going to get 3/5 is halfway between 2/5 and 4/5. I'm going to have 5/5 here, or 1, 7/5, and then 9/5. So these are my sample points that I want to use in this particular example. So my area here, as represented by this, or my net area, will be approximately my width, 2/5, times the height of each one. Now we know that this would really be 2/5 times f of 1/5 plus 2/5 times f of 3/5, etc., up to 2/5 times f of, 9/5. Okay, but since I'm multiplying the same width each time, I could pull that out in front, so I'd have 2/5 times 1/5 plus f of 1/5 plus f of 3/5, f of 5/5, f of 7/5, plus f of 9/5. Okay, so if we plug these in to our function, we'll have 2/5. Now if we plug f of 1/5 in here, I'm going to have 1/5 over 1/5 plus 1, which gives me 1/6. Then I'll have 3/8 when I plug that in. So we'd have to do a little bit of arithmetic, but these are the values that we would get. 1/2 plus 7/12 plus 9/14. And when we get a decimal approximation to this, we find that we have 0.9071. So this would be an approximation to the value of this integral. And the midpoint gives a fairly good approximation. Okay, so now that we've seen, together with what we've done in class, left endpoints, right endpoints, and midpoints, we also want to talk about now using the fact that our definite integral represents an area or a net area to compute some integrals just using geometry. So now instead of approximating the area, we'll be able to figure out the exact area because of the nature of our curve. So here my function is 1/3 x minus 2. Okay, so I want to draw that because I'm going to be interested in shading what the area is that I'm looking for over this interval from 0 to 9 and finding it using geometry. So when x is 0, I'm at -2. Let's see, when x is 9, 2, 3, 4, 5, 6, 7, 8, 9 here, we're going to be at 1 because we'll have 9 over 3 is 3 minus 2 is 1. And we're going to intersect our x-axis when this is equal to 0. So when x is equal to 6. Okay, so I can sketch this here. We'll go through there approximately. So what I'm interested in here is this net area. And this is made up of two different triangles. So I just need to figure out what the base and the height of these different triangles. So this has a height here of 2, and this is 6, this is 3, and this is 1. So my integral here is equal to negative 1/2 6 times 2, the base times the height, plus 1/2 times 1 times 3. So we've got negative 12 over 2 plus 3/2, which gives us negative 9/2, or negative 4.5 for that exact value. Okay, so we see by connecting this integral to the fact that it represents this signed area, we can compute that using geometry. But now we also know that the value of this integral is negative 9/2. Okay, so we can only do this for things like triangles, trapezoids, rectangles, but also for a few other geometric shapes. So we want to look at one more example. So here we have the integral from negative 1 to 3 of the square root of 4 minus the quantity x minus 1 squared dx. And we want to figure out what kind of curve we're dealing with so we can try to find the value of that integral using geometry. So what we're looking at here is a function where y is equal to this 4 minus x minus 1 squared. So to help us see what this curve is going to look like, it's going to be useful for us to square both sides. So I've got y squared equals 4 minus x minus 1 squared. And then if I move this over, I've got y squared plus x minus 1 squared equals 4. So we should recognize this as the equation of a circle. So remember, in general, the equation of a circle is x minus h squared plus y minus k squared equals r squared is a circle with center h comma k and radius r. So for our example, we have a center at 1 comma 0 with a radius of 2. So we can go ahead and sketch this. So I'm at 1 comma 0 is my center. It has a radius of 2. So it'll go out here to negative 1 and to 3. Let's see, and also a radius of 2. So we'll go up here. So roughly we have, let's see if I can connect this all the way over here, something like this. Try that one more time. Okay, so we have here, it turns out that our picture, now notice it was just the positive square root. The circle would have included that top half and the bottom half, but we just have the top half because our function is just this positive square root. So this integral now from negative 1 to 3 of this positive square root represents the area under this curve. But notice that that's half the area of a circle that's centered at 1, 0 with a radius of 2. So what we have here is a semicircle of radius 2. So we know that this is going to be equal to 1/2 the area of a circle. So it's going to be equal to 1/2 pi r squared. So we get 4 pi over 2, or 2 pi is that particular area. Oops. And this is also equal to 2 pi. Okay, so it's nice when we can recognize something as being able to be computed with geometry, because when we start doing integration techniques, we'd find something like this pretty difficult to compute using sort of algebraic techniques, but geometry makes it very easy. Okay. So let's look into a few more properties of the definite integral. So what we have next here is some properties that tell us how we can work with our definite integrals, how we can combine different definite integrals in different situations. So what we have here is properties of the definite integral when we are given two continuous functions. And continuous functions are functions that are integrable. Excuse me. In other words, if a function is continuous, it will be integrable. So it makes sense to talk about the integrals of those functions. Our first property says that the integral from a to a of f of x dx is equal to 0. Notice that this makes sense because in our definition, delta x here would be equal to a minus a over n, or 0 over n. So we're dealing with rectangles of width 0. So each height is just being multiplied by 0. So it makes sense that that should be equal to 0. In this second example, we're looking at the integral from b to a. Now, when we first defined our integral from a to b of f of x dx, we assumed that a was less than b, but it is possible to write down an integral where b is less than a. The relationship to the integral from a to b involves multiplying by this -1. So if we think about this, if a is less than b, then our delta x is b minus a over n, and that would be positive. But if a is less than b, then if I write down the width as a minus b over n, then that's going to be a negative quantity. So that's going to contribute that negative sign here to what we would expect. So our integral from b to a of f of x dx is equal to negative the integral from a to b of f of x dx. You can also switch it the other way around. You can say a to b of f of x dx is equal to negative the integral from b to a of f of x dx. So sometimes we'll want to switch the order of, remember these are called our limits of integration, sometimes we'll want to switch their order, and whenever we want to do that, we're going to have to multiply by a negative sign out in front. Our next property here says that the integral from a to b of a constant function is equal to the constant function times b minus a. So it helps to have a picture in mind for why this is true. So if we're integrating c, that means our function that we're dealing with is just the constant, or the horizontal line, y equals c. So the integral of c from a to b would just be the area of the rectangle that has width b minus a and height c. So that's how we get c times b minus a. Okay. So two more properties that just tell us how we can combine different integrals of functions. If I have the integral from a to b of c times f of x dx, I can pull out that constant so that it's just c times the integral from a to b of f of x dx. And if I'm going to add two different functions or subtract them, I can say that the integral from a to b of f of x plus g of x is the integral of f plus the integral of g, as well as the integral from a to b of f minus g is able to be broken into the integral of f minus the integral of g. Okay, so these will be helpful when we're trying to compute integrals, that we can break them up into these different pieces. So we want to look, so we have one more thing we want to do, and then we're going to look at an example that uses these properties. So another thing that will be useful for us sometimes is to break up an integral into a couple of different pieces by breaking it up into some areas over different subintervals. So if we have a number c that lies between a and b, so a is less than c is less than b, on an interval from a to b, then we can think about breaking up the integral from a to b into the integral from a to c plus the integral from c to b. So one picture that we can have in mind here is if I have this integral here from a to b, c is in the middle, I can talk about the area under the curve from a to c plus the area from c to b being equivalent to the area from a to b. So sometimes it'll be useful to us to break up integrals like this. Also notice that I can move this around in a few different ways. If I had a less than b less than c, so now I have something where a is here, c is at the end, and b is in the middle, then how could I talk about finding the integral from a to b? Well, the integral from a to b should equal the total integral from a to c of f of x dx minus this piece here that I haven't shaded, minus the integral from b to c of f of x dx. So this is just showing how we can kind of move pieces around here to maybe get the part that we're interested in. Okay, so let's see how this goes in an example. So in a case like this, I have certain information. I know the integral from 0 to 3 of my function is 2, from 3 to 6 is -5, and from 3 to 6 of this other function g is equal to 1. So given just this information, I want to compute some integrals based on this. So we've done various problems of this nature with derivatives, we were given some limited information and then we wanted to compute some things based on that. So this is a problem just practicing those properties. So the first thing I'm interested in computing here is the integral from 3 to 6 of negative 3 times g of x. Well, I know that I can pull a constant outside of my integral, so I can pull that negative 3 out, so that becomes negative 3 times the integral from 3 to 6 of g of x dx. And I know that this integral is equal to 1, so this becomes negative 3 times 1 for a value of negative 3. So we know that these definite integrals are just numbers, so I can substitute the value of that integral by the value that's given to us in the problem. In this next example, I've got the integral from 3 to 6 of 3f of x minus g of x. So I know that I can break up a difference of the integral of these two functions into the integral of their difference, as well as pulling that constant out in front. So I can rewrite this as 3 times the integral from 3 to 6 of f of x dx minus the integral from 3 to 6 of g of x dx. And so I know that the integral from 3 to 6 of my function f is negative 5, so this becomes 3 times negative 5, and the integral from 3 to 6 of g is 1. So I have negative 15 minus 1, or negative 16. I can do a similar thing with this piece, but then I'm going to have to do one more step. So first I have 6 to 3, integral from 6 to 3 of f dx plus 2 times the integral from 6 to 3 of g of x dx. Now notice that this is the integral from 6 to 3, and I have information about the integral from 3 to 6. So I need to switch the order of those limits, which means I have to introduce a negative sign. So I've got negative the integral from 3 to 6 of f of x dx, plus, I have to do the same thing here, negative 2 the integral from 3 to 6 of g of x dx. And so I have negative now negative 5, the value of the integral from 3 to 6 of f, plus negative 2 times the value of the integral from 3 to 6 of g, which is 1. So I end up with 5 plus negative 2, or 3. Okay. So lastly, I'm looking here at the integral from 0 to 6 of my function f. Well, I have an integral from 0 to 3 and an integral from 3 to 6 of f, so I need to add those two pieces. This is using that last property. So this is the integral from 0 to 3 plus the integral from 3 to 6. So I see that's going to be 2 plus negative 5, which gives me a value of negative 3. Okay. So these just allow us to practice using these different properties, and you'll see probably some more examples on your WebAssign homework as well. I think there's just a couple more things we want to talk about here. We also have a few comparison properties that relate to our integral that tell us what we can say about our integral if we know certain information about our function. So for example, if we know that our function is greater than or equal to 0 for all x on our interval from a to b, then the integral from a to b of f of x dx will be greater than or equal to 0. Okay, well this sort of makes sense with what we've been talking about so far. If the function lies above the x-axis, then we're talking about a positive area, because we're going to have our widths are always going to be positive and all of our heights will be positive as well. Another property that we have is that if f is bigger than g over the whole interval, then the integral of f will be bigger than the integral of g. So if f lies above g, then the area under f, this is f and this is g, will be larger than the area under g. So this is the area under g, and then the area under f would include all of that plus some. Okay, and then lastly we have a property that tells us if f of x is between two numbers, so these are some numbers little m and big M, over the whole interval, then using that let's see, the second property here, if I have m less than or equal to f of x less than or equal to m, that means the integral from a to b of m dx would be less than or equal to the integral from a to b of f of x dx, which would be less than or equal to the integral from a to b of m dx. And then if I just have a constant function m on an interval from a to b, I know that that's just the area of the rectangle with width b minus a and height m. So this is how I get my result, that the integral from a to b of f of x would have to be between m times b minus a and capital M here, times b minus a. So these properties are useful in certain situations where we're trying to get a bound on our function. Okay, so we just want to look at one example of one of these comparison properties. So in this example, we're told that f has an absolute minimum value of little m and an absolute maximum value of capital M. So what does this tell us about the bounds on the integral from 0 to 2 of f of x? Well, if f of x is no smaller than little m and no bigger than big M, then we can say f of x is between these two different values. So this tells us that the integral from 0 to 2 of m is going to be less than or equal to the integral from 0 to 2 of f of x, which will be less than or equal to the integral from 0 to 2 of m dx. So then we can say that, let's see, the integral from 0 to 2 of m is going to be 2m, because it's going to be m times 2 minus 0. So we see that the integral from 0 to 2 of f of x dx will be between 2 times little m and 2 times big M. So here we can say between 2m, little m, and 2 times big M. Okay. Please let me know if you have any questions.